So first of all, I'd really like to welcome everybody to this workshop. And this, as I'm going to show on the next, I might move on to the next slide. So basically, what we're hoping is that this is going to be the first of an ongoing series of workshops, which will operate at two levels. There will be the beginners workshops, which will be, and the first one of those is next Tuesday. Is that right?
Yeah.
Tom? Yeah. And then there'll be these more advanced ones. And the difference between the two is basically the beginners ones are going to be about trying to make sure that we can tell people the absolute basics so that they're not scared about trying to start up DataSHIELD. And then once they can go into it, they can then start identifying the particular things they want to focus on. The advanced DataSHIELD workshops, the word advanced may not be an ideal word. It's basically, these workshops are going to try and address practical, methodological, technical issues which are of realistic concern to people in the DataSHIELD community. And what I'm keen to do is to model what we're doing here on the regular life cycle meetings that Angela and CEDO have been organising around life cycle. I think, Angela, I think it's you and CEDO, isn't it? And basically, the idea is to be able to discuss and explore variety of issues in terms of analytic methods, and to explore and potentially share scripts that people have developed to address specific issues. So basically, that's what I would like to have these sessions to be about. One of the specific issues that I want to address, which isn't completely dealt with by the life cycle meetings, is that there are quite a few people from other projects, in particular ReCap, who I think would like to be able to get more access to the to this sort of support, and I'm keen, therefore, that we should provide something at the DataSHIELD level. So obviously I'm presuming the regular life cycle meetings are going ahead anyway, because I believe they're very successful. But so we have these other set that we can do centrally. And one of the things that we might want to do is, if there are particular sessions that end up being very useful, either in the life cycle ones or in the DataSHIELD ones, it may be that we can then share so that the same stuff could be covered at another meeting. Basically, although this is unrelated to life cycle, recently there have been, at two different times, there have been presentations of the work that Yannick and Juan have been doing in relation to the resources infrastructure that now exists within DataSHIELD. And that, but personally, I think it was really useful that we had multiple opportunities for people to see what was happening there, because that particular development is so important and helpful. So in terms of content, my feeling is that the primary focus initially should be statistical functionality, largely because I know there are a lot of issues that people would like to see how other people are dealing with, and also because I know that there's a lot of capacity for doing a whole series of things within DataSHIELD that most people haven't become fully aware of yet, largely because we've not been advertising it as much as we might. And so I'm very keen that we should start trying to fill in those gaps. And so I see a key emphasis in terms of trying to make sure we're dealing with statistical or data management functionality. But in addition, like the resources capability, then I think if there are major infrastructural developments that it would be useful for everybody to see, then that should also be seen as a potential target for these sessions. In my view, going forwards, these presentations in this workshop, or these workshops, should be open to anybody in the growing DataSHIELD community. And also I would suggest they might be made by anybody in that community. It doesn't have to be someone in the development team who does it. If someone thinks that if someone's done something that they think others would benefit from, then we should basically consider including that in one of these workshop meetings. And in addition, it may well be that rather than, today we've got, as we'll see in a minute, we've got 2 presentations, one about 20 minutes and one just over 30 minutes. But they don't need to be that long. So for example, if someone has a 10-minute presentation that they would like to do about something they've just succeeded in doing after working very hard at it, which is quite often the case in developing DataSHIELD scripts, then I think those should be viewed as viable candidates for things to present. So I think we can think about the structure of the meetings in some detail as we're going forward. Now, in terms of the structure of the meetings, one of the things that I would like to suggest now, and then we can discuss potentially at the end of the meeting or elsewhere, is that in order to make sure these meetings actually happen and are directed at the DataSHIELD community's real interests and needs, I'd like to try and identify a lead and a co-lead for them, ideally from different places, and I would suggest ideally not from Newcastle, so that we can really make sure that the community's getting leverage on what we're actually doing in terms of these plans. I know that certainly if it's left to me to make sure that these things happen, and at the moment, particularly because I'm quite involved in COVID stuff, then there's just no way anything's actually going to happen. So basically, I would like us to discuss that at the end of the session today. Then in terms of a more definitive consideration of how they should be structured, how they should be used, and how they should fit into everything else in the project, I think I would like this to be a subject to the discussion and modification. Once only some of you will be aware, but some will not be aware, that we are at the moment trying to implement a new community-wide governance structure for the project, with a key steering committee that will be drawn from across the groups that are involved in the project, not just the small number, particularly Newcastle, that are centrally involved in the development. And so we're talking, so Andre in particular, Andre Morgan, has been talking to us about this concept, and so hopefully over the summer this will start. And one of the things I would like this governance structure or the governance mechanism to consider is how these sorts of meetings might go forward. And in addition to these meetings, I also think we ought to consider having a freely accessible script archive. Can I ask Angela or Cedo, do you have a script archive in Lifecycle?
Yeah, we have a GitHub repository.
Okay, great, good. Yeah, that's what I was thinking of the example one. Great. Well, I think basically when I was talking about a lead and a co-lead for this, and what I'd like is a lead and a co-lead for across the DataSHIELD community that can deal both with these advanced meetings and also with some sort of scripts archive, which I agree should be in GitHub unless there's some particular reason why we shouldn't do that. So, all right, so that's basically the plans for the DataSHIELD workshop, the advanced DataSHIELD workshops. And again, one of the things we should discuss at the end of the meeting today is when the next one should be, and then we should consider the frequency of them going forward. Okay, the particular agenda for today. So first of all, you've got the delight of this welcome from me. Then basically I'm doing a presentation for about 30 minutes, which will be addressing the modeling and interpretation of center effects in DataSHIELD. This being one of the particular topics we've been asked to look at. The 30-minute presentation will be followed by questions and discussions. but my plan is that if a burning question comes up during the presentation, then feel free to, but that's stopping you understanding in terms of going forward, then feel free to interrupt. And Eleanor, is it you who's going to be watching to see if people come in, or no, or sorry, is it you or Dimitri who's going to be watching if people come up with questions?
Yeah. Dimitri's keeping an eye on the chat, so I'd say put any questions in the chat. And
well, if people, what I suggest is if people want to actually ask a question, then if you put a flag, either the hand up mechanism or a chat flag, and then we can stop me. However, if it becomes, I've various settings before, I've known this become so, there's so many questions come up that the whole thing stops. So basically, if that does happen, then we might have to row back a bit on that and try and restrict stuff to the question and discussion session. There'll then be a short comfort break. Then Tom is going to do 20 to 25 minutes on the early stages of implementing mediation analysis and DataSHIELD, which is something that he's been working on. And that again is something that's been actively asked for in a number of different venues. This will again be followed by 15 minutes question and discussions. And then at the end of the day, I also want us to we'll have 30 minutes for general discussion, the topics of the day. And then that we can also then discuss future plans for the advanced workshops and the script archiving. So that's the general plan as I see it through this session this afternoon. Now that there are two czars or guards. There's a chat guard, which is Dimitri Avram, and a time guard, Eleanor Hyde. So Dimitri will manage the chat lines that comes up, and Eleanor will check times. And Eleanor, you really must show no mercy, particularly to me, because I am known to run on. So
what I will say, we'll agree that we just have to make sure we leave enough room for Tom to start, because I don't want to cut off questions in the middle of a really important discussion. I think we just need to make sure that Tom can start at a certain time, but I would say go for it.
Yeah, great. And so the other thing to say is that slides and R scripts will be freely available after the workshop, and everything that I'm doing is there is a complete script that I'm going to be running through. So if I don't finish, then basically there's nothing to stop people afterwards going through and running it themselves. It's annotated, the script, and so these will be available after the workshop. And Eleanor, do we know how they're going to be made available, or is that something we need to consider? Is there a particular place which, again, we should, so should we put these, for example, onto GitHub?
Well, I think as long as we put them somewhere that everyone can get to without having to have loads of permissions, then we will make sure everybody gets to hear how they can find the stuff. I think that's the best way to say.
Brilliant, great.
Yeah.
Okay, so let's get on to the topic today. So I'm going to some brief initial comments, and then I'm going to basically take you through the script that I've developed to see what the key issues are. Okay, so modeling center effects in DataSHIELD. So this is when you've got multiple centers, how is it and why should you model the fact that some things may be different in different centers, and therefore you've got to build that into the analysis in some way. And in general terms, there are two broad reasons why you need to be able to implement center effects. The first one is what I call confounding by study. So confound is a variable that's related both to an outcome and to one of the explanatory variables. And confounding by study is when different studies have got systematically high or systematically low values for the outcome, as well as systematically high or low values for at least one of the explanatory variables. And this, like confounding anywhere, basically can just lead to the wrong answers. And I'm going to show you how big an effect this can have. And the reason we know this is an issue is that in the BioShare project, there was an analysis done which didn't have centre effects in, and the results were so extreme that that the overall result that you got from pooling across the studies was nowhere near the values in any of the studies. And so fortunately, the person who was involved in it asked the question and we were able to deal with it. But that demonstrated that even in real life, you can get very severe confounding by study. The other reason, apart from confounding by study, is when you're wanting to explicitly model real heterogeneity that actually exists in the causal structure or the study design. So when you talk about confounding, it's not that the actual confounder has a different effect in the different studies. It's that because of the way its values differ, that it's leading to the confounding. Whereas if you want to explicitly model the heterogeneity, you are then actually wanting to model the fact that different elements of the causal structure vary between the studies. And you might want to do this to better understand the science, because if you don't deal with it, you get bias in estimates or bias in standard errors and variance. And then there's a variety of other reasons why you need to deal with it. For example, there are some situations in genetic analysis where if you don't properly deal with underlying heterogeneity, you end up with incorrect answers in what you're doing. So basically, these are the two main reasons: confounding by study and trying to model heterogeneity. And there's a variety of reasons, a variety of examples of the modeling the heterogeneity. All right, so in terms of what you need to actually be able to do to understand and use in DataSHIELD, the practical issues and methods that I'm going to talk about are, first of all, how to create study-specific variables and IDs so that you can do study effect analysis. Secondly, we'll touch on the fact that there are these two ways of pooling data from multiple centres in DataSHIELD, one of which, a nice name that Juan suggested, is virtual pooling for this, and I like that. So this is basically what happens with DSGLM. It's basically when you're working with the individual level data remotely at each of the studies in such a way as if the data were all centrally placed. So this can be called virtual pooling, and meta-analysts tend to refer to it as IPD meta-analysis. And then the contrast to that is study level meta-analysis, where you ask each study to do a complete analysis on their own, return the answers to the centre, and the centre then does a study level meta-analysis of those answers, taking account of the estimates of standard errors, and either using a random effects or a fixed effects meta-analysis to get overall answers. Now, in a lot of settings, generally, SLMA pooling is used much more widely, particularly in genetics, but it's done by studies, a central study in a consortium asking each of the other studies to do a series of predefined analyses and to send those results centrally, and then to do the study level meta-analysis on them. The great advantage of DataSHIELD for this, and I personally think that particularly in genomics, this could become one of the major uses of DataSHIELD, is that you centrally command everything. So for example, if you didn't, once you've done say an initial genome scan, you identify maybe 100 genetic variants that you think are particularly rated to your outcome. The obvious thing then to do is to look at interactions between those and a variety of the explanatory variables. But unless you've either asked everybody to do a huge amount of analysis before it all starts, and you've asked for them to do interactions between every pair of variables, or you've been incredibly lucky in guessing, then by and large, once you've done your initial scan, you're then going to go back to the studies and say, all right, please, can you do some more analysis to do these interactions we'd like to do? But of course, in DataSHIELD, you can just command that straight away. So you save potentially a lot of time in terms of being able to do the work. The next area involves is working with and interpreting generalized linear models under heterogeneity. So this is DSGLM and DSGLM SLMA. which is the study level meta-analysis equivalent of DS-GLIM. And then finally also working with and interpreting generalized linear mixed models. And so the script that I'm going to show has all of these elements to it. I say, if I hadn't got through it all, then people can look through afterwards. And if necessary, we could arrange another session, maybe outside this thing, where if people had a lot of questions, I could be present, or maybe, and Dimitri, other people could be present to actually address the particular questions that came up. Move my RStudio configuration around so that the output now appears in mine on the top right. Okay, so first of all, we've got a key data frame called LD that contains the data that I'm actually working with to do this for this script is a survival data set, which has got, so it's a synthetic data set that was based on the one of the BioShare data sets. And it's basically got repeated measures in it so that I can show generalized linear mixed modeling as well as linear modeling. And so this shows the sort of data that there's a whole lot of variables that basically relate to the survival outcome, and then a whole series of explanatory variables, which for anybody involved in BioShare include body mass index. This is the healthy obesity project. Okay, so first of all, in most studies, most analyses, you're going to need to do some transformation, which I've got two particular ones here. So I'm creating two variables that are not factors into factors. Now, the first thing is, so we basically, I'm going to just show you, this is a generalized linear model relating systolic blood pressure to a series of explanatory variables. And I'm starting off by doing those in separate studies. So the data sources argument is critical to be used to doing study effects, study center effect analyses, because basically it enables you to focus on one study at a time, either for the analysis or for the construction of new variables. And so in this case, basically there's nothing particularly exciting here, just to say that in this case, there's no heterogeneity in that original data set. And what we basically got is we're modeling blood pressure. We find that females have got about 7 millimeters of mercury less than males. The blood pressure increases about 1 millimeter of mercury per, I can't remember if that's 10 years or 1 year, no, per annum. That's a synthetic value that I've deliberately made bigger than it should be. Then there's a relationship with whether you've got a low body mass index, i.e. below the mean, or whether you're in the obese group, which is above 30. And then finally, there's a variable from the environmental study, which was, these are particulates of size. Tom, I'm sure, can explain this better than me, but basically these are airborne particulates and a form of pollution. And age, the reason the age .60 and .16 have got dots with numbers is that they've been centralized around those mean values. Okay, so the first thing I'm going to do is, so we've got the systolic, we've got systolic blood pressure, and I'm creating a new version of systolic blood pressure I can then fiddle around with to set it up for so that we can do the analysis in a useful way. So I'm copying that and then doing some. Now, so a key element here, which is crucial, and I'm sure I'm preaching to the converted, you've got to do lots and lots of QA when you're going through creating the new variable when it gets complicated. And so that's just some QA, which is showing that the variable I created is the same as the one it was originally in that case. Now there's basically in order to do study effects, what you ultimately need is one of two things, which you then convert the second one to the first one. So basically, you either need a dummy variable, or if you've got 3 studies, you need, we'll say 3 dummy variables in each study, which are maybe called study 1, study 2, and study 3. And basically, everybody in study 1 has 1 for study 1 and 0 for study 2 and study 3. Study 2 has 0 for study 1 and 3 and 1 for study 1. So that's a set of 3 dummy variables, and in any model you would generally use 2 of those in order to allow for the effect of there being differences between the centres. The alternative, which can then be used to generate that, is to have a variable which is a single variable in the studies that takes the value 1 in study 1, 2 in study 2, and 3 in study 3. Now, rather than, okay, I'll show you the first way to do this. I won't go through the other 2 because of shortness of time. Eleanor, how long do you think it's reasonable for me to go on at this point?
I was thinking, I mean, Tom, what do you think? But I was thinking if you went on till literally kind of quarter past 2 your time, 3:15 European time, then that would give Tom time, but then you'd had a lot of.
Oh, I was sorry, I wasn't okay. In that case, I'll try and finish it quickly because I was meant to have half an hour.
Yes,
so,
you are. Well, I would say we'll try and.
Okay. If you feel as though you're going to stop me, then just give me a couple of minutes warning. All right. Yeah. So in that case, I have got time to go through this properly. So yeah. The first thing that I'm going to do is create vectors of 0, all zeros. Sorry, a vector called vect0, which takes the value 0 in all studies, and a vector called vect1 that takes the value 1 in all studies. And what I need to do is create a vector that is of the same length as the standard vector length that we're actually working with for all of our models. So the way that I've historically always done this is I've identified a variable with no missing data in it. In this case, there's a sequential ID in this data set. And that sequential ID, if I just show you. So this data set's got 2,038 observations in the first study, 1637 and 2662. That, crucially, this num-DNA is telling us, sorry, num-NA is telling us that there are no missing values in that study, and it's a numeric variable. That wouldn't actually matter in this case. And so the first thing I'm going to do is I'm going to use the make function to calculate the value of that variable minus itself. That then produces a whole series of zeros. Now you could, as an alternative, do a variable over itself to create a value of 1, but that's dangerous because if you've got any zeros in there, you get NaN returns. So it's generally safer to calculate the vector of zeros. So basically, I'm going to calculate this vector of zeros and then check that that is what I've actually got. So we've got a numeric variable of the correct length, and quantile mean is showing that that is all 0. Then to create the vector of 1s, I'm simply going to add 1 to that, and then we get vect1. Which is all 1s. And now we're going to start creating the dummy variables. So basically we need 3 variables altogether, and I'm going to call them ins1, ins2, and ins3. And the first thing I'm going to do is copy the vector of zeros into those 3 variables in all studies, using the make function again. Okay, so we've now got vect0 with zeros in every study. Then we want to, in study 1, we want to simply take the values of that vector of the ins1. We want to replace them in that study. We want to replace them with 1 rather than 0. And so this is where we start using the data sources. So this command says copy what's in vect1 into ins1, but only do that in study 1. And then the other 2 then do the equivalent in study 2 and 3. So this basically now ends up with what we needed. So basically we've got these 3 variables, each of which takes the value 1 in the study it refers to, and otherwise 0. And then just to check that we've got good answers on that, we'll get a QA check. One thing to say, some of you may not be aware, there's now a new table function called DSTable, which does work. It's rather easier to use than the other ones, and it will do 3-dimensional tables. And so in fact, in this particular 3-dimensional table, we can see that when the in S3 study is 0, which means you're either in study 1 or study 2, then in study 1, all the values are 1, and in all the studies are 0. When S3 is 0, in S1, in S2, yeah, sorry, both, sorry, when S3 is 0, both in study 1 and in study 2 take the value 0. And then when S3 equals 1, then the study, sorry, I'm just ridiculously lost here. Sorry, I'm being stupid. So the first one, when in S3, then basically in study 1 they're all 1, in study 2 they're all 2, and then if S3 is 1, which is i.e. in study 3, then both study 1 and study 2 are 0. So basically it has been created correctly. Right, the second method to do this equivalent is to create a client-side vector holding n in each study, and so that's not what I'm going to do there. So basically what I'm going to do here is I'm going to create a vector using DSSEEK. So DSSEEK creates a sequence of numbers, and basically I'm going to base this now on the variable PM10.16, which does have missing values in it. So we can't use the method I showed above. So these are the missing values in it. And so what we do is, first of all, we want to use DSSEEK to calculate a sequence, which in this case is a sequence starting at 1. It's incrementing it by 0, so it remains at 1 all the way along. And then by saying along with name PM1016, it says do that right along the length of PM1016. So in each study, this is going to create a vector of 1s that is the same length as PM1016, which is what you want. So this is I'm going to call this VECT12, which means it's the second version of VECT1 because we've already created VECT1 before. And basically, we can see that that's creating a correct vector of 1s. I'll just show you again that way. And now we're going to do the opposite to what we did before. So now we're going to create the vector of 0s, which we're going to call VECT02, by subtracting 1 off that VECT1. So basically, that's 2 ways to create a vector of completely 1s in every study, a vector completely 0s, and then if you use the methods I showed on the first method, then you can then use that to create those sets of dummy variables. Then the third way to do this is to basically, first of all, work out how many observations there are in each study, and if you use this length command followed by an unlist, you basically get a vector which is the 3. So I was covering up something on my screen, which basically are this is now a vector containing the 3 lengths of the studies. And now we're going to use DSREP to create vectors of that right length, that correct length in each of the studies. And so basically, and what that's going to, the first one, I'm repeating 1 all the way down. The second one, I'm repeating 2 all the way down. The third one, I'm doing 3 all the way down. So this is effectively a study ID variable that is in each of the studies. So it's taking the value 1 in study 1, 2 in study 2, etc. And then we're going to go through a series of things on. So we're basically going to do that, convert it into a factor. But the key issue is that what we ideally want to, as you remember, we wanted to create those dummy variables that were ones in the study concerned and zeros otherwise. Now, in fact, you can't do that with a factor. The reason you can't do that with a factor, and this is something that I wrestled a lot with when I first started doing this, and I suspect other people have probably had a similar problem. The reason you can't use a factor is, although you can tell DataSHIELD that in each study, although it's only observing one value in its variable, nevertheless, it won't create a factor that can be used in any model unless there's at least two different values on that thing. It requires there to be some sort of contrast in there. And so you can't use it as directly as a factor as you would if it was any other variable. But so what the DSAS factor in DataSHIELD basically creates a series of dummy variables that is equivalent to a factor. And I'm just going to show you what happens with that. So basically we've, I can't remember if I've done this or not. I'm just going to. Yeah, so that's all the QA flying through and it's all fine. Then we're going to create the values of this thing, and basically SID, which is basically the created from the by saying that we want to do fixed dummy variables is true, ends up here being in a data frame. And if we look at the three, so basically the three variables in that data frame are called DV1, dummy variable 1, dummy variable 2, and dummy variable 3. And again, as you can see from before, in study, when in studies 1 or 2, then they're either all 1 in study 1 or all 2 in study 2, and in study 3, they're all 1 in study 3 and 0 for the others. So basically, using this combination of things, again, we've calculated the equivalent of what I showed in the first example. So basically, we're in a position to calculate these vectors we need. All right, let's now actually have a look at some analysis. And what I'm going to do here is I'm going to actually recreate the SBP variable, the systolic blood pressure variable, in the same way as it was originally. And as you'll see, it's made as a combination of multiplying male female by -7. We're multiplying age 60 by 1. We've got a variable that's multiplying the body mass index as a quantitative variable by 0.75. We're then adding 140 to it to get a value that's a realistic sort of value for systolic blood pressure. And then finally, we're going to add 2 random effects to it. The REC is basically an individual level random effect. So basically, this is a variable that we use in analysis later on to be able to look for when the results are correlated within an individual. And the REE is simply a random error that comes in at the end, and so makes the regression model a meaningful sort of regression model. So if we just run all those things through there. And just to show you the sort of thing that we get out from it. So the one we just created here is, so basically the 5th percentile is 106 millimeters of mercury, the 95th percentile is 157 millimeters of mercury, the mean's 132. So this, although this is far from a perfect simulation of blood pressure, it's nevertheless looking reasonably sensible. And this just here shows that these are exactly the same results as we got in the original data set when I originally created this for all the work that we've done. Now, first thing we're going to look at is confounding by study. So in order to introduce confounding by study, what we're going to do is we're going to deliberately perturb one of the key explanatory variables, so the age 60, which is age centered around 60. And to do that, again, we're going to work within each study. We're going to add 19 to age 60 in study 1, subtract 21 in study 2, etc., and write this out so there's a new variable with the new center called age C, which will vary then in its center between the studies. Now, these should have the same length as the standard vectors we were using before. Secondly, let's just look at the quantile means on these. So we can see that it's all sensible. Now, one of these is slightly premature because I basically at the start of this, I read in the worksheet that I created and I ran the whole thing. And in fact, the systolic one here isn't actually created now until this next thing here. So let's see how we just perturb the systolic blood pressure. So we perturbed the explanatory, we're now going to perturb the outcome. And basically what we're going to do is again do this study by study. And the thing that I'm changing here is that when instead of adding 140 in each study, I'm adding 120 to the systolic in study 1, 169 in study 2, and 138 in study 3. So basically we're doing a very simple introduction of a fairly serious level of study confounding. Okay, and now let's just to see what effect that's had. First of all, let's look at the systolic blood pressure. And what it's basically done, you can't see it very well on this scale, but effectively, instead of there being one line which shows the a one-to-one relationship between systolic, the variable systolic, and systolic blood pressure, there are actually 3 lines that are basically perturbed vertically by the amount that we changed the value we were adding on. And then similarly for age, it's a bit easier to see on this one. So basically, again, we can see that there are these things. So this is a very simple form of dealing with or introducing confounding by study. So let's see what the results of this actually do. So first of all, we're going to fit the standard GLIM in each study. First of all, using the original age variable and the original outcome variable, and then we're going to use the perturbed outcome variable and the perturbed age. And then we'll look at what we get as coefficients out from the 2 of them. And crucially, what you find, so first of all, I'll print those again so that they go right across the screen. All right, so the first thing that's clear is that there is a difference in the intercepts, which is what you'd expect because you deliberately perturb the intercept. But then apart from that, you'll see that shifting of age had no impact at all on any of the other covariates. You get exactly the same answers. So that's what you should basically get, and we'll find exactly the same thing happens on the other 2 studies, but we won't look at that in detail. So basically, if you do within study analyses, then you get answers very similar to what you originally simulated. And in particular, the thing to notice here is that the age effect is around 1, so it's just a bit below 1 in this, with a very narrow standard error. Okay, now let's fit the whole. Now let's fit this the GLIM on all the data simultaneously. Right. So first thing to see is that the estimates for the when you use the original systolic blood pressure, i.e. without within study confounding, are still the same. And basically, again, that value is close to 1, and it's got a narrow standard error. Now let's look at the study where we base. This is now doing a GLIM, pulling all the studies together to analyze this, but without including a study effect. And the first thing to see is that the key point is the value for age now is nothing like what it was originally. It's much, much lower. And the standard errors are a bit wider, but the key thing is that this is basically much, much lower. And crucially, it's what this result is way outside the values in any of the individual studies, suggesting that something weird is going on in terms of confounding. And so this is an example of the fact that if you don't deal properly with confounding by study in some way or other, you are going to potentially get very wrong answers for things. And as I say, although this was deliberately simulated as a big effect, which was likely to cause a problem, in fact, as I say, we have had a real example from real data that would have potentially been published if we hadn't picked it up, where this led to exactly the same thing on that real data, with the overall result being outside the range of any of the studies. All right, so how can we, well, actually, I'll just show you the reason for it if we look here. Right, so the reason is, so basically the original data, so if we plot the age and the systolic blood pressure, we end up with this nice relationship, which clearly is consistent and analyzes with a gradient that's 1, though I noticed I've done age and systolic blood pressure the wrong way around here. But what happens in the others, when you do the other analysis, is you've actually got a separate cloud of points for each study, and therefore what happens is that pulls the gradient much flatter. And in fact, it would have been quite easy for me to do a set of results that would have actually made it go negative. So basically, you can see that this can have a big impact. So how are we going to deal with this? And so now we can make use of our INS1 and INS3 variables that we created earlier. And I'm simply going to add them as covariates into the model. So again, I'm doing one model for systolic blood pressure, the original, and one for the modified one. And now let's look at the answers. So, so now you can see that obviously this one is the original variables still produce the same answer as they did before. But now we've got these study effects in, we also getting exactly the same answers from the pooled the analysis across all the studies. So basically, in this case, for dealing with within study confounding that's generated in the way it's being generated in this case, and simply putting in study effects as effectively extra intercepts completely gets rid of the bias in the estimates, with the exception of the intercept itself. So that's one way of dealing with things. Okay, this next picture simply shows that it's the same if we use one of the other methods of creating the ones and zeros thing that we showed earlier. This just shows that. So in the previous model, we basically had the dummy variables for study 1 and for study 2 and study 3 in. If we put study 1 and study 2 in, then again all of these other variables still have exactly the same covariance. So it doesn't matter which of the two dummy variables which studies the dummy variables come from. Now, so now let's see, is that we didn't generate there being any difference in the age effect between the studies. Let's put an interaction in to see whether we can find an interaction. And the key point is that as well as providing the ability to deal with the within study confounding, these study level variables also allow us to look for heterogeneity between the studies and the values of particular things. And so what I'm going to do here is put interactions in between, where are we? Yeah, so between between age and study 2 and age and study 3. And so let's again look at the results we get from the outcome. Even worse than before. Okay, and basically, if we look at the interaction terms here, so in the down here, we can see that they're very small, they're non-significant, and it looks like there is not likely to be any particular evidence that there is heterogeneity in the effect of age. So there's study confounding by study, but not actually any change in the values of the things. That's what we simulated. Now, so here, in order to try and say, is this significant, I'm doing a bit of an arm wavy stuff, looking at the estimates and their standard errors, and the ratio between those basically compared to a normal standard deviate, or squaring them, comparing it to a chi-squared, is what's called a Wald test. And we can see that neither of these are significant at all. But the other way we could do this is as a formal likelihood ratio test. And to do that, then what you need to do is, well, so take the model with the intercept, with the interaction in, we get a residual deviance and a residual degrees of freedom for it. From it, first of all, we use those to scale the deviance. And so basically, if we take that divided by that, that's then the scale deviance. We then look for changes in the scale deviance between the model with the interaction and the model without the interaction. And so first of all, this is the actual difference in the deviance, 101.2. And then if that difference is scaled by that scale parameter, we then end up with a value which effectively can be now compared to a chi-squared on 2 degrees of freedom, because it's because that's the way that the deviance works in terms of a likelihood ratio test. And then we get a p-value for that, which confirms what we thought vaguely from the Wald tests, that basically we're getting a non-significant p-value. All right, now the next way to deal with the with the fact that there's this problem with the heterogeneity, it's to use a pooling via SLMA. So basically, we're going to use, so rather than doing an overall model that is pooled using the virtual pooling, we're now going to do an analysis using GLIM SLMA, which is basically fitting the model separately in each study, bring the values centrally, and then doing a study level meta-analysis using Metaphor to do that pooling. And so, where was the model? Right, so, and a key point to, so this is the model without the interaction term in. I'm just going to show you that so what happened is that the SLMA returned a whole series of values, which included an output sum, which contains variables that can then be analysed within Metaphor using the RMA function, the random effects meta-analysis function. Then the server-side function also returns number of valid studies, and then the beta matrix for overall and for each study separately, the standard error matrix overall and for each study separately, and then the basically as well, if there are any studies that have been excluded for any reason, then it gives you the valid studies only, the valid standard error matrix only, and then finally automatically it will produce a if you've asked it to do a metaphor pooling, it will take the output summary and do an SLMA pooled estimates matrix to get the answer overall. And if we now look,
we have a question, Paul.
Yes, certainly.
Do you keep the study dummy variables in the SLMA model?
Do I keep the study variables in the? No, you don't need. Well, no, in fact, you can't, because basically each study is fitted on its own. Then a vector that's all noughts or all ones or any number won't fit, because it basically what you'd have to invert the variance components matrix at the last step, and that would be singular. So basically, the fact that you can fit these variables that are all ones or all zeros in using DataSHIELD and DSGLM arises from the very unusual setting that when DSGLM works, what it does is it asks each study to do a single iteration simply in order to generate the information matrix and score vectors. Those then get sent centrally, and basically this keeps happening backwards and forwards, and there is no inversion of the variance covariance matrix until everything's converged, and that's done centrally. So basically it's the study level variables are fine for DSGLM, but if you put one of those in straight into an SLMA or just a study analysis of that single study, it would not work. It would blow up basically. So just to show you, I'll just focus on the, so these are showing from each of the studies. We've got the estimates from the 6 covariates from each of the studies. We've got the, I mean, we can see that that the intercept is much higher in study 1 than in study 2, for example. So even though we've not got study effects in there, it is allowing that to actually happen. Then we got standard errors. These get pulled across, and then the RMA function within the DataSHIELD GLIM SLMA function then produces 3 models by default. One where we're doing random effects meta-analysis pooling using maximum likelihood. Then another one using random effects meta-analysis using REML, which is basically then meant to be unbiased. And finally, it does a fixed effects pool meta-analysis. As we'll see in a minute, the fixed effects pool meta-analysis, the answers you get from that are very similar to what you would get from the overall GLIM in terms of its standard errors, if you had the overall GLIM with the study effects in. So basically, these two approaches are very equivalent to one another. Now, I'm just going to now show you the output from this random effects meta-analysis. You can look at in more detail. And so basically what you get from the output from this is, so for each covariate, and I'm going to focus here on I'll focus on PM 1016. All right, so there's basically the values for the individual studies for this look pretty similar, particularly when you compare them in relation to their standard errors. And the test for whether there's any heterogeneity for this variable PM 1016 is is very non-significant. There's no evidence of heterogeneity between there. Now, in a minute, we will contrast that with what you get when you deliberately built heterogeneity into what's happening. So, key point is that when there is no random effects, when there are when you use the Glim way with the study level effects in, the overall Glim virtual pooling with the study level effects in, the answer you get allows you to, if you've got put the interactions in, allows you to do a likelihood ratio test that tests whether or not a variable is actually got effect modification between the different studies. And in our case, the pooled, the likelihood ratio test was non-significant. And then at the same time, you can do the same thing from the SLMA by looking at this test for heterogeneity. And although they're not identical, they are generally of a very similar magnitude. All right, now, so is that okay for me to keep going at the moment, Eleanor?
Myself? I was just thinking, you've probably got about 9 more minutes.
Okay, so I'll just quickly whiz through this. And so, okay, I'm not going to explain why I've just done that, what I'm doing there. It doesn't really matter, but I'm doing it. So what I'm now going to do is I'm going to generate a new value of systolic blood pressure, which explicitly has a different effect for PM10-16 in study 1, study 2, and study 3. So basically, study 1 is lower than the overall one was, study 2 is higher than the overall one was, and study 3 is slightly higher than the overall one was. So basically, I'm deliberately synthesizing an effect modification across the studies. Okay. And this new variable that's had that effect modification is this variable systolics. It's got an X on the end of it. And I'm just gonna, I won't look at the study specific results because they're neatly summarized in what we then get from the overall ones. Okay, so first of all, now let's fit 2 GLIMs. The first one is predicting the study, the SPP variable, but without that variation in the PM10, whereas the systolics one is has got this inbuilt impact of the variation in the PM10. So let's put those up, show that again. Okay. Okay. So the first thing is that we can see that the overall the estimate from PM10-16 is higher when you've not done that, simulate the different values, and it's lower when it isn't. But clearly, it's not telling you what the correct value for those are. So what we're now going to fit is two models, one with the study effects in but no interactions, and then secondly, study effects with interactions. Now, so first of all, the study effects with interaction. So basically, you've had to have the the study level variables in there. They're now being put in as interacting covariates, and we can see the fact that the study 1 has got a higher level for PM10, and then the study 3 has a lower level, and these are looking as though, but they're small, and in fact, in this case, this happens to be by chance because this is the SPPX, not the one that was simulated. But now let's look at the two systolics ones. So these are the ones that were.
You've got 5 more minutes, Paul.
Okay, great. So basically, we can now see that in the one that was deliberately had the interaction, the effect modification built in, we can now pick that up easily. You can see that both of those things, one is clearly significant, one is getting on for significant. And if we now do likelihood ratio tests, then first of all, for the one where there was no effect modification, then adding that effect modification didn't improve the models significantly, whereas in the other one where it did, we've got a value that is significant now. And now to finish off, let's look at the SLMA pooling. And so this is pooling for the SLMA. So first of all, this is the systolic blood pressure directly, so the one that didn't have the effect modification in it. And if we look now for the test for heterogeneity of the PM10 variable, we can see that there is no significant evidence in 2 degrees of freedom for that being there being heterogeneity. But if we now look at the where's the other one gone? Oh, yeah. So first of all, that's the same as before. That's not right. Where are we? So I'm confused by that. It certainly wasn't doing that earlier. Oh, right. So now we can see that there is a big difference between them, and crucially, the test of heterogeneity. If you remember, the other one was 0.016. This is about 0.014, and so basically, again, we can see that by using the SLMA approach with then looking at the test for heterogeneity, we end up getting very similar answers to what we can get instead by doing a standard GLIM fit under virtual pooling with an interaction and doing a likelihood ratio test on the interaction. So I won't share any more now. What I'm going to suggest is that the next bit that this all covers, which you could work through on your own, is basically all about starting to work with generalized linear mixed models. Now, I think it might be good to have a session on that anyway. And so one of the things I wonder is whether we should think about the next session being about using generalized linear mixed models. And people can look at this ahead of time, then I can go through it on the day, and then we can basically go ask detailed questions at that point. Okay, so I will stop at that point. So are there any? So how do we want to do this? Do you want questions then now, Eleanor?
We did. I think we should maybe step over to Tom. Otherwise, he's going to have no time for his presentation. I think we did have questions coming through in the chat. I don't know if everybody's completely been kind of baffled by the amazing complexity, or is had followed everything. I would say if you have got questions, do type them in the chat, and I think Tom will answer them as he goes. Demetrius will be following the chat. So shall we? Do you mind, Paul, if we move on to Tom?
No, not at all. No. I'm quite happy. I mean, one of the other things I'd like, basically, the level at which it should be presented is one of the things that would quite like to discuss, because what is the best way to go through this sort of thing? And if the way I've done it is too detailed and almost impossible to follow, then we should say that, and then we can then change that.
Yeah, all feedback is welcome, and we do have a beginners workshop next Tuesday. So if this is if you're thinking, okay, I'm not quite at this level yet, then we do have another workshop. So, but I think you've all heard about that. I think there are some more questions coming through. So unless Demetrius has answered that.
So why don't we do Tom, and then we can come back and then discuss everything with any questions anybody's got.
Yes, let's do that.
So I'll stop sharing.
So I've started sharing. Hopefully you can see that. Yeah, great. Okay. So I guess my name's Tom Bishop, and I'm a senior data scientist at the University of Cambridge. And just to give you a bit of background, I've been working with DataSHIELD for several years now, and DataSHIELD has been central to our Interconnect project that's been run from Cambridge that investigates causes and ways of treating diabetes. We've managed to publish a couple of papers from our analyses that have run on DataSHIELD, and one of these analyses involved an investigation of a variable that could have potentially mediated an association between an exposure and an outcome. And this was a couple of years ago, and at the time we wanted to solve this problem with the functionality that was available in DataSHIELD. So I appreciate that the method I'm going to show you today is perhaps one of the simplest approaches you can take to mediation, but we took this approach to be pragmatic and to try and to complete our analysis with what was available. And the feedback that we've been getting from some of the groups that are using DataSHIELD is that it would be useful for me to walk through the steps that I took when I did the mediation analysis a few years ago. So yeah, I'm always one to sort of get my excuses in early. So I don't pretend to be, I'm not like a mediation guru. So I'm not an expert in mediation, so I apologize if I don't get some aspects of it quite right or over explain some things that are really obvious to you. But that said, I guess perhaps my strength is that I have used DataSHIELD quite a bit. I've also been quite short of time recently, so I have had to borrow quite heavily from David Kenny's website, and I borrowed the example data from Virginia University. So the plan for this presentation is I will give you a brief overview of the Barron and Kenny method, which is the kind of recipe that I followed. I'll then kind of introduce the data set and then walk through the steps that I took to apply the Barron and Kenny method in DataSHIELD. And then I'll talk briefly about what the future might hold for mediation, as much as I can, given my limited knowledge about it. But maybe that can be the seed for some discussion. And if there's any questions, I can either take those as we go, or we can cover those at the end. So this is the kind of the Barron and Kenny method as I understand it, and without wanting to sort of trivialize it, it really is just fitting 3 regression models to your data, and then one kind of statistical test at the end to confirm whether you've got mediation. So the first step that Barron and Kenny recommend is to test whether you do actually have a kind of relationship between your exposure, which I've called X, and your outcome, which I've called Y. So that's perhaps a good place to start, that maybe your exposure influences your outcome. You then might at that stage suspect that actually there's some variable that mediates that relationship. So your next regression model that you would fit would be between your exposure X and your mediator M. Again, this is just a simple regression model, and you check whether that coefficient is significant or not. Your third step then logically is to check whether your mediator actually influences your outcome, but you don't just fit a model of M to Y, you also include X in that model, your original exposure. And what you'd expect to see if there's grounds for mediation occurring is that your B coefficient between M and Y, you'd expect that to be significant, and you'd expect the size of your and significance of your relationship between X and Y to have decreased. So that would suggest that actually this effect is occurring through the AB path, the indirect path, rather than the direct path, which is C. So if you've got this far, you're thinking that there probably is some sort of mediating effect, but you still need to prove whether that's significant or not. And I know that the kind of the literature and there's a recommended approach to that is to actually do bootstrap replications of this A and B relationship and establish your standard error for that pathway using bootstrapping. But given that with DataSHIELD we have this kind of client-server relationship, if you wanted to fit a model multiple times when bootstrapping, that could be slow. So we chose just to go for the Sobel test, which is slightly less preferred, I know, but it was a means of establishing whether mediation potentially was occurring. And that test is just given by the square root of this formula here. That gives you the standard error of the AB indirect pathway. So overall, that's what I understand the Barron and Kenny method to be, is 3 regressions and your Sobel test. So here, this is the example data set that I'm going to demonstrate through DataSHIELD. It's not exactly the data set that I did my actual analysis on, but it has the same structure and the same sort of mediation relationship. So in the synthetic data set, we have students' exam grades and their happiness. And we suspect that actually it's not really the grades themselves that directly affect their happiness, it's actually that their exam grades affect their self-esteem, and that in turn affects their happiness. So that's our sort of mediation pathway. So I'll move on to DataSHIELD. And as this is the advanced course, I'm not going to show you logging in or anything like that. I've got the data in 2 locations, and I've logged into the servers, and we can look at a summary of that. So you can see there's 2 studies, and each data set is pretty small. It's only got 50 participants in each one. And in each data set, there are 3 variables, as I showed on the diagram: the grade, the self-esteem, and the happiness. They're all continuous variables, just integer values between 1 and 10. So I think there are 2 ways that you could do this mediation analysis based on the kind of great explanation that Paul has just given, where you can do your IDP, the virtual pooling way of doing things, which is where you attempt to fit single model across both data sets at the same time. I'll show that one first and then briefly run over the study level meta-analysis equivalent where actually we fit a model to each data set and then meta-analyze its results as part of our Barron and Kenny steps. So the first steps we have to do is that initial establishing whether, well, does the grade actually really have any relationship with the student's happiness at all? So for the IPD, we just use the standard GLM formula function. Here's our formula looking at grade and happiness. It's, as I explained, it's all continuous data, so we use Gaussian, and we fit that, and that runs, and we can see that for grade we've got a coefficient of about 0.4 with a small p-value, so we sort of have grounds to suspect that grade does affect happiness. So what about our mediator? So now we need to do that next step, which was to look whether grade actually influences our mediator, which is self-esteem. So all I've changed is the formula. Then fit that single model to both studies, again with the GLM function, and we've got coefficient of 0.56 and again a small value. So grade does look like it influences the mediator, which is self-esteem. So then our third step, our third regression model, is testing whether the mediator does affect our outcome. So does self-esteem affect our happiness, and correcting for grade at the same time. And what if mediation is occurring, we expect to see the coefficient of grade getting smaller and to see a significant coefficient for self-esteem. So again, I'll fit that model across all studies. And what we see is that our grade coefficient is now only 0.04, so it's definitely got smaller to our first model. It's no longer significant at 95% level, yet our self-esteem coefficient definitely does look like it's significant. So we've got grounds to suspect that there is some sort of mediation mechanism going on. So now we need to turn to our fourth step, which is our Sobel test, which tests whether that indirect pathway, the sort of AB on my diagram, whether that is significant. And I'll do that by confirming that the indirect effect, comparing the lower bound 95% confidence interval to 0. So I calculate the indirect effect, which was AB, just by multiplying the coefficients together. And then I've ahead of time typed out the horrible Sobel equation. So I use that to calculate the standard error of the indirect effect. And then I calculate the lower bound of our confidence interval on that indirect effect. So I expect that, I'd like that to be greater than 0, which it is. So we can be confident at a 95% significance that there is some kind of mediation going on. So I think you can do the same thing if you wanted to do things using the study level meta-analysis way of fitting each of your regressions. So we can do exactly the same thing using the same steps and the same formula, but this time using the SLMA variant of the GLM function. And we can tell it to do the meta-analysis and combine the models fitted to both studies for us. So I can run that. So looking at the coefficients for our grade, it's sort of quite similar to what we got from the virtual pooling. So it's about 0.4, and with that standard error, it's significant. So there is a relationship between grade and happiness again. We then look at our exposure and our mediator, as we did with the other one. And again, with that effect size and that standard error, we think that there is a significant relationship between grade and self-esteem, the exposure and the mediator. And then we can fit our final model using the SLMA. And again, the grade coefficient has shrunk to about 1/10 of the size. And with that standard error, it probably isn't significant, yet self-esteem looks like it is significant. So again, we have this same grounds to suspect that mediation occurs. And with those effect sizes and standard errors, I can repeat the steps that I did before to apply this Sobel equation longhand. And we see that our lower bound 95% confidence interval is greater than 0. So we can suspect that the mediation is occurring. So one sort of quick enhancement that we could do to this process that Demetrius has very kindly put together for me is to hide this horrible Sobel calculation where it's quite easy to make a typo in a more friendly DataSHIELD function. So we can literally just run this mediation test function where we tell it what our mediator is, we tell it our independent variable, we tell it our dependent variable. And if we run that, we get a more sort of user-friendly result for our Sobel test, this time separately each study. In both cases, our p-value is less than 0.05. So that's the end of the sort of the DataSHIELD demonstration. I said that I would try and illustrate where it might be possible to go next for those of you that want to do more advanced mediation analyses. I've already shown you that we could simplify that Sobel test so that you don't have to type out the formula every time. I talked about the fact that it was preferable to bootstrap your indirect effect standard errors, and I still think that might be possible, especially in the SLMA setting, because I think you could do your bootstrap iterations on each study, pull all the estimates back, and then use those to calculate your standard errors. So I think there's some scope to improve that. Longer term, I know that there have been some initial discussions with some of you who do much more advanced things, such as conditional effects in the presence of sequential mediators with interaction between exposures and mediators. So I know that that requires some more advanced things that can normally be found in the Medflex and the mediation packages. And it's my understanding that it should be possible to replicate some of that functionality in a DataSHIELD setting, but we've kind of got to the stage now where it needs to be more fully scoped out, and to sort of agree who will do that work, how it will be funded, and those kind of things. So I think that's all I had to say. I don't know if we've had any questions or whether we can just discuss.
Yeah, basically there are two questions for mediation analysis. The first one is, what are the values of Royman and Goodman numbers in the mediation test function? And basically we have converted the same function from native R that does similar tests as the Sobel one, but with slightly different formula of calculations. So we just report those two in case that anyone want to use them. The other question is, considering the limitations of Barron and Kenny method, are there plans to expand that to counterfactual based methods? I'm not sure if you want to say anything, Tom, but what I want to say is that we are in a discussion with the users that they want to do mediation analysis, and we are looking what functions from R are most commonly used. So if you know any functions that do these specific counterfactual based methods, we are happy to have a look and see if we can implement those in DataSHIELD.
Could I add something to that? Tom, do you want to, are you about to say something, Tom? Could I add something to that?
I was about to say that I would have to go and learn about counterfactual based methods. So no.
Well, so the situation is that I'm completely sold on the fact that we definitely need to expand the capacity to do these causal structure modeling things better. One of the specific problems that one of the specific issues that needs to be addressed is we obviously have to have a priority for what we're going to implement. And at the moment, one of the questions is, one of the things that's been said to us is that there's a group that for whom the priority is to introduce a particular package, the name of which I've forgotten. But Dimitri, can you remember what the package is?
Medflex.
Yeah. Now, so and the problem that we've got with that one is that it's actually been discontinued on updating by R. So what we would really like is input from the user community, both about what aspects of the causal structure modeling you'd like, as well as if we then, the easiest thing to do to get functionality in quickly is to be able to implement a package. And so it would be good if we could basically get input on, if we're going to go for one package to start with, which one would you like to do?
One question about you, Paul. Is the computational time the main reason for choosing one of the two methods? I mean,
it's so quick. It really doesn't make any difference. That it's more, I think it's more an issue of how used you are to creating variables in DataSHIELD using the make function. And some people are not very experienced with it, and some of them are. And that's really why I gave the 3 different ways of doing it. One of the issues to be aware of, which is something, is that if you end up with if a make function has got a complicated set of brackets, you really need to make sure that you check your output correctly to make sure that you're not getting an incorrect answer. And then you may need to break the analysis down or the transformation into a series of steps. And in fact, that happened to me yesterday when I was preparing for this, and that there was a very straightforward make step that involved adding 4 things together with multiplication inside them. And basically, one of the ways of doing it just produced totally weird results. And the only reason I found that was to keep checking it. So, but if you do get into one of those situations, if you break the analysis down, it always ultimately works, but you should be aware that that's a problem. But it really doesn't matter which of those methods you use.
Just to quickly follow up on that, I mean, I asked the question. So it would make no difference even if we were analyzing, I mean, huge data sets, because now we were talking about, I mean, few thousands of observations. But even if it were millions, I mean, pooling the analysis or doing separately would make.
Oh, sorry, I'm misunderstanding what you're saying. Sorry, I apologize. You're basically saying comparing the virtual pooling to the. Okay. Okay. No, there is so basically the SLMA approach is much quicker generally. Well, not much quicker, it is quicker. And then,
because you do a separate analysis and then pool everything on the server, and then they will make that. I mean,
yeah, so per pool on the client, yeah. And the I've actually, my own position on this has moved almost totally. So when we first started off, I was virtually always doing virtual pooling, and that's how we're developing things. Now my view is that, in fact, the need for doing virtual pooling is probably fairly limited. There are some situations when you should, but by and large, you get almost the same answers with the other one, and it is quicker. And to be honest, a lot of groups, like for example, genomicists who work with multiple studies, they tend to be used to using study level meta-analysis anyway. So that, you know, really there's a whole series of reasons why it's easier. At the moment, the key function this relates to is the generalized linear mixed models. So we've got a generalized linear mixed models thing and with SLMA up and running. And in fact, I've got a series of extensions to that to allow a whole series of other things to be done at the server end, which will be useful. Then in the background, we're working on producing the virtual pooling method, but we're not putting as much emphasis on that because we know that the SLMA one is really answering a lot of the questions that you need to do. Basically.
Thank you.
I mean, does anybody else have a view on that? Has anybody used both approaches in any particular setting? Okay, I mean, it doesn't surprise me that people have.
We used the SLMA method in Interconnect exclusively, and one of the other benefits is if I've got this correct, you don't need to harmonize all your confounding variables as well.
Yeah, so basically, because the random effects meta-analysis is mopping up some of the sort of uncertainty that's in there, then you can end up with consistent estimates or more consistent estimates with appropriate standard errors for them. So, for example, in one of the examples which I didn't get on to in terms of showing you, there were a couple of variables that had heterogeneity in them. And when you then pulled them using study level meta-analysis, the standard errors you got out from that become appropriately bigger to reflect the fact that there is that extra level of uncertainty there. So, and then the other thing to say about study level meta-analysis is basically using the SLMA approach, you can do virtually put any package virtually into DataSHIELD, because all you're asking it to do is to fit that package that we know fits on a single study normally, and then basically return the results and pull them. So it is much, much easier for developing new functionality. So the way I see it going forward is that we'll probably be focusing a lot on doing that and then only doing virtual pooling in special situations. Having said that, Dave Corty has put a special request in for he would like mediate analysis to be available in a virtual pooling way, and so that is one of the things we need to bear in mind, that specific request has actually been made.
So I've used both approaches, and the only thing with the SLMA is sometimes if you're doing subgroup analysis, you don't have the same amount of power as when you do the virtual pooling.
So basically what you're saying is in some studies, I could see that, yeah. So basically, particularly if you had combinations of subgroups that one was common in one study and rare in the other way around, that you could end up with, I can see that would be a problem, yeah. So what do you tend to do, Angela? What is your approach?
I would prefer to do SLMA, because you can also, I think you can see the variation a bit better as well.
Yeah.
But because I do experience some power when I'm doing subgroup analysis, I'm experiencing some power issues, then I have then done the virtual pooling as well.
Yeah, no, I think my only concern in that situation is that almost if you really have a low power on the SLMA, then you almost start to worry, what is it that the virtual pooling method is managing to grab from somewhere in order to increase that power, and what assumptions are being made. So, I mean, in general, I do just feel more confident, as you say, with the SLMA approach. And I think it may be that if we all continue to believe that, maybe we ought between us to write something to suggest that, because most people who do use DataSHIELD know more about the virtual pooling one, because that's the one we tended to push historically, and maybe we ought to shift the emphasis slightly. So any other questions from anybody? Is there anything on the chat, Dimitri?
Not any questions.
Okay. So in that case, first of all, can I ask the question, in terms of how we should present these situations? I really like what Tom presented. I thought that was just exactly correct. I wasn't happy with necessarily the way I presented mine. And do you think it would be, should I have reduced the amount of detail I was focusing on doing code, rather, and sort of basically have a script that people can then look at without me having to go over it in detail? What do people think? It was so confusing that nobody thinks of it.
Paul, I would say actually, when we're going to send everyone the presentations, all that kind of stuff, we are going to actually send a way of giving feedback as well.
Okay, great.
The open lab thing. So if people feel happier to write it down or whatever, I'd say
yeah, fine.
Use that opportunity, because as I say, we have got the beginners workshop next week, but this is also for people who know how to log in, who know what they're doing with DataSHIELD,
yeah,
and are after the kind of really nice fancy functionality. So so yeah, any input you can give us is great.
Okay.
So yeah, there are other options.
Sorry. The other thing I wanted to ask about is that, which I personally feel that the answer should be yes to this, is that, so in preparing for this, it was clear to me that there was a lot of stuff around the generalized linear mixed models that people really would benefit from hearing about. Because if you've not used a lot of the things that you need to do in terms of using generalized linear mixed models, even if you're doing it using R, using just the native functions, there's quite a lot of issues to be aware of. And I do wonder whether people be interested in there being a later one of these meetings that focused on doing the generalized linear mixed modeling. What do people think?
If I can say something, so as a total beginner in DataSHIELD, so in the beginning I didn't understand that this would have been a series of workshop. So I thought that I thought, okay, so there's going to be the advanced one. I said, okay, I'll try to grasp something from there, and then on Tuesday follow the beginners. But I mean, looking at this, at the description of the two, the beginners one was a lot of focus at, okay, we'll teach you how to log in and do this kind of stuff. I said, or maybe I can skip that and move directly to the advanced one. I didn't thought that it would have been so so precise. So I mean, so on a specific topic. So you would have shown us something that is very specific, which was interesting, and from which I did learn a lot of things, or I mean, started learning things of how DataSHIELD work. So I mean, this was very interesting to me. Maybe, but probably I'm only, it's because I'm on the wrong series of workshops. But maybe an introduction on how DataSHIELD works. I mean, what are the things that you can do with DataSHIELDs that are not only, as I was thinking, at a place where, I mean, you could store data in a proper way and use it in collaboration with others, but also it also can be used as an analysis tool. I mean, is something that I discovered today, and from which I'm very interested in. Also, if I'm more a Stata user than R, but I mean, it was very interesting.
Tom, did you look like you were about to say something to that? You had your arm in the air. Okay. I mean, we have to work, basically, well, there's a number of options for us. Because that will naturally fall into the beginners. Part of the beginners sort of system should be to discuss those things, as well as how you actually in practice use it, to try and understand how it actually works. I mean, is it too complicated to have two sets of workshops? I mean, and that maybe we shouldn't call them workshops, because it just seems to me that this is like continuing education for people involved in DataSHIELD, and call it a workshop makes it sound too big. Whereas really, you know, if these things say occurred once a month or something, I think it'd be fairly easy for us to keep finding topics that people wanted to discuss and would be amenable to people presenting stuff. And so and it may be that we should just have workshops, which will include some beginner stuff and some other, or we should continue with 2 different sets. I mean,